lesson 61 sequences, and then we'll also go through the appendix from lesson 61, simplifying decimal equations. First off, let's review what a sequence is. A sequence is just an ordered list of numbers. And these numbers of the sequence we call terms. So terms are just a list of numbers in a sequence. And there are different kinds of sequences we have. We have arithmetic sequences, which means you're listing the listing of terms with a constant difference from one term to the next. So you're adding the same number. Or you could think of you're subtracting the same number. If you are adding a negative, you're really just subtracting that number each time. Geometric sequences are listing of terms with a constant ratio between the terms. So you're multiplying the same number each time. And the same number each time, but it may look like you're dividing, because if you're multiplying by a fraction, like if you're multiplying by 1/4 each time, really you're dividing by 4 each time. So think of arithmetic sequence, adding or subtracting. Geometric sequence, you're multiplying or dividing each time. Let's take a look at some examples here. Describe the pattern in this sequence and then find the next 3 terms. So it goes 3, 6, 9, 12. Well, I know to go from 3 to 6, I'm adding 3. Going from 6 to 9, I'm adding 3. From 9 to 12, I'm adding 3. So since I'm adding the same number each time, we would say this is an arithmetic sequence. And the next 3 terms, if I add 3, I get 15. Add 3 more, and I get 18. Add 3 more, I get 21. Second one, what is the constant difference in this sequence? So here, I'm adding 4, adding 4, adding 4. So the constant difference is you're adding 4. Now, one other way you could find out is you take the second term and subtract the first term from it, and you get 4. And you just keep doing that down the line. So 9 minus 5 gives you 4. 13 minus 9 gives you 4. That's another way of thinking about it as well. Next one, describe the pattern in this sequence and then find the next 3 terms. To go from 1 to 3, I could add 2 to both. Now I have to see if I do 3 plus 2. 3 plus 2 does not give us 9, so if I would have to add 6 here to get 9. Since they're not the same, I know I can't add. So the other one, I know I'm not subtracting because my numbers aren't getting smaller. So what if I did times 3? 1 times 3 is 3. 3 times 3 is 9. 9 times 3 is 27. So this is a geometric sequence. Because I'm multiplying by 3 each time. So if I multiply by 3 each time, 27 times 3 would give us 81. 81 times 3 would give us 243. Times 3 again would give us 729. Those would be the next 3 terms of that sequence. And the last one on the slide, what is the constant ratio in this sequence? Well, I'm multiplying by 5 each time. And again, to determine it, I can take the second term and divide it by the first term, and I get 25 over 5, because remember that's a ratio. That would give me 5. And 125 divided by 25 would also give me 5. So the constant ratio is we're multiplying by 5. Next sample problems. Terms have a position. Use n and a value, you use a. Create a table to help find the equation. Write a formula that describes this sequence. So a is, we got 3, 6, 9, 12. A subscript n means what is the position, which term are you referring to? for this one. So if I look at my numbers here, 1, 3, 2, 6, 3, 9, 4, 12. How do you go from a 1 to a 3, a 2 to a 6, 3 to a 9, 4 to a 12? Well, I know I'm multiplying by 3 each time. So if I take my n and multiply by 3, that will give me my a. So a subscript n equals 3 times the n. And I can prove that by taking, if I have a, and I want to find the first term, I would take 3 times the 1, and that would give me 3, which is what we have. The first term gives you 3. If we were trying to find the second term, 3 times 2, that would give us 6. Here's the second term. Multiply by 3 gives me 6. And I can keep going down the road. So the formula would be a subscript n equals 3 times n. The next one, write a formula that describes this sequence. 1, 3, 9, 27. So like I have the first term multiplying by 1. The second term, you get a 3. The third term, you get a 9. The fourth term, I get 27. We hit a pattern or a sequence like this one earlier. We said that we were multiplying by 3 each time. So here we're going to have a base. So it can be an exponent. It's going to have a base of 3. But the term is going to be up here. So it'll be the nth power. But 3 to the first power here does not give us 1. Because 3 to the first power is 3. But if we take n minus 1, now I put the 1 in for n, because n, remember, means the number of term. 1 minus 1 is 0. 3 to the 0 power is 1. Anything to the 0 power is always 1. If I put a 2 in here, 2 minus 1 is 1. 3 to the first power is 3. So this is 3, 1 minus 1. This is 3, 2 minus 1. This is 3, 3 minus 1. This is 3, 4 minus 1. And 3 cubed will give you 27. So our rule would be a subscript n equals 3 raised to the n minus 1 power. So 1 less than the term that you're finding before. Let's look at some other practice problems. Write the first 4 terms of the sequence described by the formula a subscript n equals 2n. So they give us the formula. We need to plug in our numbers. So if I plug in the numbers here, so 2 times 1, that gives me 2. Here, n is 2. 2 times 2 is 4. Here, n is 3. 2 times 3 is 6. N is 4 here. 2 times 4 is 8. So we would have 2, 4, 6, 8 there. This next one, write the first 4 terms of the sequence described by the formula a subscript n equals 2 to the nth power. So 2 to the nth power, 2 to the first power would be 2. 2 to the second power would be 4. 2 to the third power would be 8. 2 to the fourth power would be 16. So each time we are multiplying by 2 on that last one. So let's review sequences. We want to match the sequence with the type of sequence it is. We got 1, 2, 4, 8, 16. So if we look at this one, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So you're multiplying by 2 each time. So this one would be geometric. Next one here, 2, 4, 6, 8, 10. Here I'm adding 2. Here I'm adding 2, adding 2, adding 2. That would be an arithmetic sequence. And this last one, Here, I'm adding 3, I'm adding 5, adding 7, adding 9. But you also notice these are perfect squares. 1, 4, 9, 16, 25. Next one would be 36. This is neither of those two. This would be a different type of sequence. So this one, we would just say is neither. Next one, looking at the appendix, lesson 61. So this is a review from an earlier lesson. Multiply each decimal number by the biggest power of 10. That will remove all decimals. So if you don't want to work with decimals throughout here, we want to remove them. So in order to remove them, we look at the one that has the the most decimal places. So that would be 0.004, has 3. So if I multiplied all of these by 1,000, so 1,000 times negative 0.2, I would have to move this 3 places, 1, 2, 3. So this would be a negative 200 plus 1, 2, 3. This would be plus 30x equals 1, 2, 3, 4. Now we can solve this one. I can add 200 to both sides. And now I have 30x equaling 204. The x by itself, divide by 30. And I would have an answer of 204 divided by 30 gives us x equaling 6.8. So the reason why people would multiply by a power of 10 is just to make the math numbers a little bit easier, not have to worry about decimals until you get to your answer. Next one, here I have 3 decimal places here, so again I'm going to multiply by 1,000. So always count how many decimal places. The number of decimal places tells you how many zeros in the power of 10. So I have 3 here, the most, so that would be 1,000. So I'll move the decimal point 3 places to the right. That would give us 9x. 3 to the right, 1, 2, 3. That would give us 400. 3 to the right, 1, 2, 3. That would give us negative 310. Add 400 to both sides. That would give us 9x equaling 90. Divide by 9 both sides. X would equal 10. And our final set of problems. Doing the same thing, but now we have ratios here. So in order to get rid of the decimals, we'll do the same thing. So I'm going to multiply everything by, there's only one decimal place, so multiply both the numerator and the denominator by 10. So that'll give me 51 over 3 equals 340 over 10x. And now we can solve for this one. We cross multiply. So 340 times 3 gives us 1020. So 1020 equals, cross multiply the other direction. And I have 51 times 10, which is 510x. Divide by 510 on both sides. 1020 divided by 510. X would equal 2. And the last one over here. One decimal place, multiply everything by 10. So that would give us 32 over 24, the same as 10x over 180. Now for this one, I can easily reduce 32/24. If I divided this by 8/8, that would give me 4 over 3, which is the same as 10x over 180. And then I could actually multiply, if I multiplied 3 times 60, that'll give me 180, but I'm going to cross multiply here. So 3 times 10x is 30x. 4 times 180 gives us 720. And if I divide by 30 on both sides, x equaling 24. That is our lesson today on sequences and using decimals to solve our simplifying equations with decimals.